In this video we shall see more rules of finding integrating factor. Here we see rule 4. If 1 by n into del m by del y minus del n by del x is a function of x alone, say fx, then e to the power integration fx dx is an integrating factor of the differential equation m dx plus n dy equal to 0. So here m equal to x square plus y square plus 2x and n equal to 2y. So we find del m by del y equal to 2y. When we are finding del m by del y, here x is constant and here del n by del x equal to 0 because here y is constant. Hence the equation is not exact because del m by del y not equal to del n by del x. Now according to the previous rule, we find del m by del y minus del n by del x divided by n, that is equal to 1. Now this 1 can be regarded as a function of x. So the integrating factor equal to e to the power integration 1 into dx, so that's equal to e to the power x. So multiplying by integrating factor, the equation becomes this, which can be shown to be exact and whose solution as usual shall be e to the power x into x square plus y square equal to constant. This equation is also not exact equation. So for we find 1 by n del m by del y minus del n by del x equal to 2x, which is a function of x, and we find integrating factor e to the power integration fx dx, that is equal to e to the power integration 2x dx, that is equal to e to the power x square, and multiplying by integrating factor, the equation becomes this, and we can find the general solution. And finally we get the general solution e to the power x square into x square minus 1 plus y to the power 4 equal to constant. Rule 5. If 1 by m del n by del x minus del m by del y is a function of y alone, say phi y, then e to the power integration of phi y dy is an integrating factor of the differential equation m dx plus n dy equal to 0. Here we see an example. For this differential equation, we find del m by del y that is not equal to del n by del x, so it is not exact, and we find del n by del x minus del m by del y divided by m, that is equal to 6, can be regarded as a function of y alone. Therefore the integrating factor, it is equal to e to the power integration 6 dy, that is equal to e to the power 6y. Now you can check this equation actually that is exact or not. So for exact equation, we have already seen how to find the general solution, and finally we get the solution this. In example 2, here we see this equation is also not exact equation, and we find this 1 by m into del n by del x minus del m by del y, that is equal to minus 4 by y, and say that is equal to 5y. So the integrating factor is equal to e to the power integration 5y dy, that is equal to 1 by y to the power 4. So if I multiply by this integrating factor, the equation becomes this, and that is the exact differential equation, and we can know how to solve that exact differential equation. And we finally get the solution. In rule 6, if mx minus ny that is not equal to 0, then 1 by mx minus ny is an integrating factor of the differential equation m dx plus n dy equal to 0, where m and n we know the function of x and y and can be written in the form this. So if we see m in this particular form and n in this particular form, then we shall use rule 6. Here you see from this problem we can write m like this, that is equal to y into f1 xy. We can take y out from this bracket and the remaining portion is a function of xy. Similarly, n equal to x into f2 xy. Again, mx minus ny that is equal to xy into f1 xy minus f2 xy, that is not equal to 0. Then the indicating factor will be 1 by mx minus ny according to this rule, that is rule 6. So the indicating factor equal 1 by 2xy into x square y square plus 1. So multiplying by integrating factor, we get the equation. That equation is exact and we know how to find the solution. So finally we get log x by y plus tan inverse xy equal to constant. Now you see another approach to solve this equation is we can write m dx plus n dy equal to half into mx plus ny into dx by x plus dy by y plus mx minus ny into dx by x minus dy by y. If you simplify this expression, you will get m dx plus n dy. Now if I divide it by mx minus ny, we get 1 by 2 mx plus ny by mx minus ny into this, and plus here mx minus ny is there, so we get only this portion. Now you can express this term in the bracket as d log xy, and here you can express this as d log x by y. So you get, so for the given differential equation you get m dx plus n dy by mx minus ny equal to this. What is this? That is d log xy plus d log x by y. Now that is equal to 1 by 2. Now you see d log xy, it can be written as dxy by xy. So we put it here, and in the numerator there will be a xy term that will be cancelled out, and we finally get this dxy by x square y square plus 1 plus d log x by y. You just try to do it yourself, how we can come from this line to this line, and the required solution will be tan inverse xy plus log xy equal to constant. In rule 7a, you see when the equation of the form like this, when m, n, r, s are constant, then it has the integrating factor x to the power r minus 1 minus m into y to the power s minus 1 minus m into f x to the power r y to the power s, where f is any arbitrary function of x to the power r y to the power s. When the equation is of the form like this and mn1 minus m1n not equal to 0, then the integrating factor will be of the form x to the power h y to the power k, where we can solve this equation for h and k and we get the unique solution. Because mn1 minus m1n not equal to 0 we have assumed, so that's why we get the unique solution for h and k. In example 1, we solve this equation and we see this equation is of the form this. So we compare alpha, beta, a main with this equation and we find the values of alpha, beta, alpha 1, beta 1, a main, m1 and n1. So by using rule 7b, we get these two equations. If we solve these two equations, we get h equal to 2, k equal to minus 3. That's why x square y to the power minus 3 is an indicating factor of the given equation. And the general solution is this. In example 2, we solve this equation. Similarly, we compare alpha, beta, a main, alpha 1, beta 1, m1, n1, and we find values of alpha, beta, n, and alpha 1, beta 1, m1, and n1. If x to the power h, y to the power k be an indicating factor, then we get these two equations by using rule 7b, and we solve this equation for h and k. We get h equal to k equal to 1. xy is an indicating factor of the given equation and the solution is this. Here I have given some exercises for you. You must try these exercises